There's kind of two main ways of understanding math, and they do feed off each other, but at the same time, a person could be good at one but not the other, or vice versa. And what I'm thinking of is conceptual understanding versus problem solving. In class, you do want to understand concepts. It is important to have conceptual understanding. That's what we're going to work on first here today. But you do want to be able to translate that to problem solving. You know, people who do well at AP calculus exams, oftentimes they're good at problem solving, but it doesn't mean they completely understand what they're doing. They're just good at solving problems, good at getting good grades. Kind of makes people mad, right? They get good grades, but they may not understand everything. They may not see all the connections. On the other hand, there are some people who understand high-level concepts pretty well, but they have trouble translating that into doing well on exams, homework and exams. They have trouble with the problem solving, putting it into practice. It is important to be working at both of those skills. But let's focus today first on conceptual understanding by showing you some Mathematica graphs and animations that illustrate some of the ideas that we've been talking about with motion, parametric curves, and also what I was talking about the other day is flow and flow rates. So the example in this section, you could write this down if you like, is going to be one-dimensional motion. The velocity, or which will be equivalent to the speed here, is 3t squared. And the integral of the velocity will be the distance traveled, f of t equals t cubed. If you want to write that down, you could write, I'll go ahead and write it down here. So the velocity, well, okay, let's write it. Yeah, okay, I'll write it as v of t. That's the velocity. That's 3t squared. Since that function is not negative, it's greater than or equal to 0, it is the same as the speed in this example. This is one directional motion, not back and forth motion. The distance traveled will be the integral of the velocity. And it is important that you understand that you can write this as a definite integral, not just an indefinite integral. We're not just after an arbitrary antiderivative, but a particular antiderivative. And the way to do it is to, well, if your starting time at t equals 0, put the lower limit of integration to be 0, make the upper limit of the integral a variable. I have mentioned this before. That's something that can be done. If t is fixed, then this is one integral that you could compute. You could compute an area. Maybe you could do a left or right-hand Riemann sum to approximate the area. But in the end, I change my perspective and say, hey, t can be anything. So I could do this integral over any interval, and so I could think of it as giving me a function of t. But if you do this, you really should call the variable something different here, like a u or something. When you do that, then you call u a quote-unquote dummy variable. Why? Well, in a sense, all variables are dummy variables, but it doesn't mean anything. I'm just trying to use a different letter than t to emphasize the true variable for this function f of t is that upper limit of the integral. If I go ahead and now evaluate this integral by replacing v of u with 3u squared and use the fundamental theorem of calculus, antiderivative of 3u squared with respect to u would be u cubed. U goes from 0 to t. I then get t cubed minus 0 cubed. I get t cubed. And you say, yes, that's an antiderivative of the speed, of the velocity. It is going to give us the distance traveled, which again, since this is one directional motion, will be the same as the displacement as well. It's only with back and forth motion that things get tricky. So that's how you could write it symbolically. Let's look at how to illustrate this with Mathematica, the connections between these graphs. First, I've got a static graph here to illustrate these connections. So the graph on the left is the velocity, the speed. The graph on the right is the position, Back in chapters 2 and 3, we started with the graph on the right. We started with the position. If we know the position, how do you find the velocity? You take the derivative. So this would be our position graph over here on the right. And we said the slope of that curve at any point gives you the speed. The derivative at any point gives you the speed. So what I've got here at time 1.3 as an illustration is I've got a little red line that represents the tangent line to the curve at that point. That point is 1.3 comma 2.2, meaning after 1.3 seconds have gone by, I've traveled 2.2 units of distance. The slope here of this line turns out to be 5.1. That's the speed, 5.1 units of distance per unit of time, meters per second, perhaps. The speed or velocity in this case is the output of the derivative when t is 1.3. The derivative is 3t squared, right? The derivative of t cubed is 3t squared. When you plug in 1.3 into that function, 1.3 squared times 3 is about 5.1. The second coordinate of this point on the velocity graph is giving you the slope of that red line. But now with integral calculus in chapter 5, we go the other way around. We say if we start with the velocity, 3t squared, we can integrate to find the position or distance traveled. And it's the area under this velocity curve that gives you the value of the distance traveled curve. This area that's shaded pink here is about 2.2. You should maybe check to see if this seems right. If this were a triangle going up like this, its base would be 1.3 and its height would be close to 5. 1/2 base times height. Let's see, 1.3 times 5 would be what? Like 6.5. Half of that would be 3.25. This is not a full triangle, so its area's got to be less than 3.25. It turns out to be about 2.2. The area under that velocity is the value of the position graph, 2.2, when t equals 1.3. But there's nothing special about 1.3. I could have done this for any time. And this animation illustrates that. As I let time vary, the relationship always holds no matter what. No matter what time I happen to be, if you know the position graph, the slope of the tangent line at any moment in time gives you the value of the speed or velocity. Its slope is 3t squared, the derivative of t cubed. On the other hand, if you know the velocity, 3t squared, the area under this graph from 0 to t is t cubed, and that gives you how far you've traveled. It gives you this position graph. There's this inverse relationship between them. Probably the hardest part to understand is how does the area give you the position? You know, maybe that's the hardest part to understand. We did hint at that by thinking about approximating distances traveled as rates times times over small intervals of time, giving you small distances traveled, but then you add those all up, meaning you add up all the tiny areas of tiny thin rectangles to get the total area, which matches the total distance traveled. Now, again, you may be sitting there saying, yeah, I guess I kind of get that. But then if I asked you to restate what I just said 1 minute from now, you'd probably forget, right? It's something that you can kind of get 1 second, but then a minute later, you've forgotten. You've got to rethink about these things consistently if it's going to stick in your mind. Here's another example. This one's a parametric curve, kind of a strange parametric curve example. If you want to write down these equations, f of t is t cubed minus 3t. That'll be the x coordinate of this example. I'll write it down on the paper up here. X equals f of t equals t cubed minus 3t. Y equals g of t equals t squared minus 2t. I am going to look at the Mathematica, but let's do some hand calculations here as well. If those are your parametric equations, this would mean the position vector is r of t. It has components f of t comma g of t, t cubed minus 3t, comma t squared minus 2t. The velocity vector, v of t, is the derivative of the position vector, which you find by differentiating each component individually. Differentiate t cubed minus 3t, you'll get 3t squared minus 3. Differentiate t squared minus 2t, you'll get 2t minus 2. And the acceleration vector, a of t, is the derivative of the velocity vector, which is the second derivative of the position vector. The derivative of 3t squared minus 3 is 6t. The derivative of 2t minus 2 is 2. And we could graph these things. We could also figure out the speed. Here in two-dimensional motion, speed is definitely different than velocity. Velocity is a vector quantity, meaning at any moment in time, it's got a certain direction and a certain length. A velocity vector can change if the direction changes, or if its length changes, or both. For circular motion, uniform circular motion at a constant speed, it's just the direction that changes, not the length. But I could be speeding up as I go around a circle, faster and faster, and so it could be changing in length as well. Anyway, the speed is the length or magnitude. I'll use the word magnitude today. Magnitude, same as length, of v of t. And again, that means use the Pythagorean theorem. Take the square root of what? That's f prime of t, and this is g prime of t. The general formula is square root of f prime of t squared plus g prime of t. That's just the Pythagorean theorem to find that length, which for this example is going to be the square root of 3t squared minus 3 squared plus 2t minus 2 squared. And yeah, I could simplify that. I'm not going to bother. It would be the case that the distance traveled, the speed is a function of t here. Just like before, you should understand that the distance traveled is found by integrating the speed. We are integrating the speed here, not the velocity vector. We're finding a distance traveled, not a change in position. Could we integrate the velocity vector? If you can differentiate vectors, can you integrate them? Yeah, you can. And if I integrate the velocity vector, it will give me the change in position as a vector. Maybe I start here, watch my fingers here. Maybe I start right here and then I go all over the place. Maybe it's even three-dimensional motion. It's a bug flying around in space, starting here, ending over there. What's the change in position? It's an arrow from the starting point to the ending point. Boom. That's the change in position. If you integrate the velocity vector, you would get that change in position vector. It's true. I haven't done an example, but I could. But if you integrate the speed, you get the distance traveled. And just like with the one-dimensional motion, you'd want to make the upper variable of the upper limit of integration a variable. And call the variable for the function that's the speed something else, like u. Would this integral be easy to do? It doesn't look like it. We'd have to integrate this square root. I bet that's a pretty hard integral. I think it's probably doable, but it's pretty hard. Let's see if Mathematica can do it. There is, I'll ignore that. Let's see here. Where am I? Got to enter this. Oh, no, close that. Enter that. Mathematica. What is the integral of the speed? Indefinite integral. Oh my, of course, that's obvious. Negative 1 plus t times the square root, blah, 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 blah. What's this? Arcsinch? Is that an H at the end there? It is an H. It's not arcsine, it's arcsinch. What's arcsinch? It's the inverse function of the hyperbolic sine function. What's the hyperbolic sine function? It's in section 3.7 or 3.8. One of those two sections, we skipped it. It was the section we skipped. Hyperbolic sine function actually is a linear combination of exponential growth and exponential decay. Why do we call it hyperbolic sine? I'll let you look into that. That's its inverse function. It's not a typo. That H needs to be there. Arcsinch. Crazy. Who would ever do an integral like that? Well, if we had to do this problem, we do that integral. Is this possible to do by hand? Yeah, but it's a pain. Yeah, actually, if hyperbolic sine is somehow exponential functions, hyperbolic arcsine, arcsinch, is actually a logarithm in disguise. I'm not going to go into details. What is the motion here? Why is this a strange motion? Watch it here. Because the blue curve is the motion. It's got a corner to the graph. Look at that. There's a corner there. That's why it's strange. What happens at that corner, that cusp? I got the vectors in the picture. The blue vector, that's the position vector. It's like a pen tracing out the curve. The red vector, that's the velocity vector. It's always tangent to the curve and pointing in the direction of motion. Notice as time goes by here, it's getting shorter and shorter. The motion's slowing down. At that cusp, it's hard to tell, but the velocity vector becomes 0 at one instant in time, right there, essentially, before it turns around. And then it turns around and goes off this direction. The pink vector, that is the acceleration vector. Yes, somehow the red vector is telling you the rate of change of the blue vector, and the pink vector is telling you the rate of change of the red vector. I'm not going to go into details. That's for a mechanics class. It is good to think about in a mechanics class. Okay, kind of an interesting motion. Is this motion, the fact that there is a cusp in the motion, reflected in any of the other graphs, like the graph of the speed? Yeah. If you graph the speed, it's got a cusp. And what if we wanted to integrate the speed without trying to deal with that expression there? We could do numerical integration. We could try left and right-hand sums, averaging them, or ask Mathematica. Mathematica, what's the integral of the speed? Oh, say from negative 2.5 to positive 2.5. Actually, that, because I'm doing that, I'm imagining negative 2.5 as being the starting moment in time. Yes, strange, but that's what I'm doing. This gives the distance traveled to be close to 30. And it is the area under this graph, even though it's got a cornering, even though it's not differentiable at t equals 1. So yes, strange things can happen. Now you might say, well, you know, that kind of motion is never going to happen in real life. And you might be right. At least not exactly, though it might be approximately right. However, at a higher level, all this stuff can be applied, and was originally applied by Newton especially, to study planetary motion. It's called celestial mechanics. Isn't that a beautiful name? The official name of studying planetary motion is called celestial mechanics. Now, this is classical physics, and if you know anything about modern physics, like relativity and quantum mechanics, they sort of look at classical physics and say, hey, yeah, that's not accurate. It's what Newton did and Newton's contemporaries. And they're right, it's not completely accurate, but it's still pretty good for most applications, like sending spaceships to Mars, for example. Getting calculations right with that kind of thing is important, right? I don't know if you remember about 10 years ago. You old enough to remember something 10 years ago? Maybe it was longer ago. Some engineer miscalculated something and the spaceship flew right on by Mars because there was a miscalculation. They were trying to get it into orbit around Mars. They miscalculated, cost millions of dollars, that miscalculation. Anyway, there are laws of planetary motion, Kepler's laws in particular, that were actually discovered before Newton. Kepler's laws about how the planets move around the sun are purely empirical, observation-based, not really so theoretical, not based on more abstract general laws like Newton's laws of motion, like F equals ma, for example. These are empirical. One law says, called the law of the ellipses. You don't have to write all this down. You can just enjoy it. I'm going to show you something that I hope you'll enjoy. There's something called the law of the ellipses, which essentially says the orbit of a planet is an ellipse with the sun at one focus. What's an ellipse? Basically, it's an oval shape. What's a focus? Not going to go into detail. It's a special point inside the ellipse. Is it really? Is the Earth really going around the sun in an ellipse? Yes, but it's an ellipse that's almost circular. It's very close to circular. You might be happy to know. Actually, this is kind of interesting. Do you know why it's winter in the winter? Because here's a conundrum. When it's winter in the northern hemisphere, we're actually closer to the sun than when it's summer in the northern hemisphere. Did you know that? So why is it winter if we're closer to the sun? You got it right. Yeah, it's the angle, it's the tilt of the Earth, which causes the sun to be at an angle that's lower in the sky. It's not as direct of a sunlight. During the summer, you know, the sun's higher in the sky. During the winter, it's lower in the sky. That's the reason why it's winter in the winter, even though we're closer to the sun. It's not enough to make a significant difference in the temperature. But we are a little closer in the winter, so that's related to this law of ellipses. Anyway, there's also something called the law of equal areas and equal times. The position vectors here, pointing from the sun to a planet, sweeps out equal areas and equal times. What that effectively means is that when we're closer to the sun, we move faster than when we're further away from the sun. Because to sweep out an equal area when you're closer, you'd have to go faster. This is more extreme with comets. You got a comet that goes really close to the sun, then really far away. It goes really fast when it goes near the sun. It's kind of like a slingshot effect. There's a really old Star Trek movie, maybe even newer movies, where they slingshot around the sun to go back in time. Well, you can't go back in time, but they go faster when they slingshot around the sun. When the comet gets far away from the sun, it goes slower, which is why it takes so long to come back. Really eccentric orbits. The ellipse is a really long and skinny ellipse for comet motion. And there's something called the law of period of motion, which does have an equation involved that involves the universal gravitation constant as well as the mass of the sun, I believe. Yeah, okay, mass of the sun. T is the period of the orbit. How long does it take to go around the sun? A is called the semi-major axis, which is related to how far it is from the sun. Anyway, without getting into details, basically what this says is planets that are closer to the sun go a lot faster than planets that are further away. Mercury goes around the sun really fast compared to Earth, compared to Jupiter. And it's not just because Jupiter has so much further to go, it's actually traveling slower. Is it? Actually, I'm not positive of that, but its angular velocity is certainly slower. The amount of angle it goes through in any unit time is slower when the planet is further away. Anyway, Newton essentially developed calculus to prove these rules from his more abstract laws of motion. It's not easy, but that's what he did. Though if you read his Principia Mathematica, that's what it was called, it's not an easy read. People have taken what Newton's done and made it more streamlined. Newton is very classical in his notation and ideas and terminology, and it's confusing. Anyway, I got more stuff in this notebook that you can read about. I'm not going to explain it, but what I want to show you is something kind of cool here. You can use differential equations to make tiny planetary systems. Essentially, this is calculus. This is differential equations for one thing. Not explaining. Creating a tiny planetary system that follows Kepler's laws, it turns out. That blue planet is going around that yellow sun. Is that Earth and the sun? No. Earth's orbit is not quite so eccentric. But this is following Kepler's laws. It is going slower when it's further away, like now, and faster when it's closer. It is on an ellipse. with the sun at a focus. And it is sweeping out equal areas and equal times, though that's difficult to know for sure just looking at it. Those arrows that are in the picture, kind of skinny arrows, are position vector, velocity vector, or acceleration vector. One interesting thing about the acceleration vector is it always does point at the sun. There's a little arrow there from the Earth always pointing toward the sun. That's related to Newton's laws of gravitation, that the acceleration vector is parallel to the force vector. It's got to point directly at the sun. You can add other planets to the picture as well. So here I got two planets, one closer to the sun than the other. The one that's closer goes around a lot faster. This is a toy solar system that is still following Kepler's laws. Okay, maybe I can make it go slower to see it a little easier. Okay, and these ellipses don't have to be parallel, so to speak. They're not here. That can happen. You can make three-dimensional pictures as well. I made a three-dimensional picture for this, just for the sake of fun of it going around. And then you can rotate this a little bit to see the three-dimensional effect. So again, I'll post all this on Moodle. You can play around with it if you like. You do have to enter all the code before you'll see the animations. So make sure you enter each line one at a time. Here's another example that I hinted at last time. Flows and flow rates with a particular example. And a particular animation. Don't worry about the particular graphs I'm using with the particular formulas I ended up using. I want you to understand the concept of what's going on here. We'll run the animation and we'll think about it. For fun, the water's both red and blue. So blue is the water that's in the tank, and red is the water that's either flowing into or out of the tank. I'm starting time not at 0. It looks like I'm starting at time -3. It just happened there. What do these graphs represent with the tank? I hope it's pretty clear that the blue graph is telling you the volume. It goes up and down. That blue graph, that black dot in that blue graph goes down when the volume goes down and goes up, like right now, when the volume goes back up. The red graph is the flow rate. It's the derivative of the blue graph. It's telling you how fast water is going in or out. When the red graph's real high, like now, lots of water is coming in real fast. Visualized as a thick red stream there. When water is going out very fast, that's when the red graph's negative and large, like right at the starting time, right about now, then water's moving out very fast. The red graph's height, positive or negative, is telling you how fast the blue graph and the amount of water is going up or down. The red graph is the derivative, the rate of change in the blue graph. It's telling you the slope of the blue graph. Conversely, the blue graph is the integral of the red graph. Notice that I'm shading areas on the red graph between it and the horizontal time axis. When those areas are positive, they contribute to growth in the volume. The integral is positive. When the areas are negative, like now, they contribute to decay in the volume. The flow rate's below, it's a negative flow rate. The integral is negative in this case. So the volume, change in volume is negative. So what I'm trying to get across in illustrating this is a visual of what we talked about the other day, illustrating that integrals are much more general than just position, velocity, and acceleration. Going the other way, actually, acceleration to velocity to position. It's much broader, the applications. You can talk about flow rates of water and the change in volume. You can talk about flow rates in money and the change in money in your bank account. Same principle. Different units, same principle. Integrate the rate of change, you get the total change. Integrate that red graph, you get the change in the blue graph.